Okay, today we're going to do lecture 4, which is on the geologic evolution of Latin America. Now, geology isn't in the title of this course, but the reality is you cannot understand the things that we'll be talking about in Latin America without a strong sense of its geology, and in particular, how the modern plate tectonic regime has affected Latin America. So we're going to, in the next two lectures, today, this one and the next one, we'll first be going through some basics of plate tectonics, and then we'll get down into the nuts and bolts of the geology of Latin America. So let's get going. Okay, so here we have a slice of the Earth. We've cut it down from the surface, where we live up here, to the middle of the Earth, the core, and we're seeing the three major subdivisions of Earth. On top, the crust. Underneath it, the mantle, which is about 45% of the Earth's thickness. And then below that, the outer core, which is liquid iron, and the inner core, which is solid iron. And so Earth is got a tremendous temperature gradient between the surface. We're quite comfortable here at 20 or 30 degrees centigrade. And the center of the Earth, which is 5,000 or something, unimaginable temperatures. So heat is always flowing from the interior to the surface. And there's a number of ways that it can do this, which is called convection. And so plate tectonics is a style of convection that's particularly interesting and unique to Earth. Next. So this results in a couple of interesting things. One of them is called the lithosphere, and another one is called the asthenosphere. These are kind of unfamiliar words, but lithosphere is the strong upper mantle. It is basically, it transports heat by conduction. That's not too important, but this is the plate of plate tectonics. This is the thing that moves sideways, which we'll talk about. And underneath this is a different layer called the asthenosphere, and it's a weaker region of the mantle that lets the lithosphere move on top of it. And it transports heat by convection, which isn't so important, but these two things, the lithosphere, which is the plate of plate tectonics, and the asthenosphere, which is the surface, the weak part of the interior of the Earth that allows it to move, are critical. So let's see, next. So again, the lithosphere is the plate of plate tectonics. And one of the interesting things is that oceanic lithosphere gets thicker and as it ages and cools. And asthenosphere, on the other hand, is, as we said, what allows the plates to move. Next. Okay, so there's three types of plate boundaries. One of them is called convergent plate boundary. Another one is called a transform plate boundary. And the third is called a divergent plate boundary. So a convergent plate boundary, as it implies, is where two plates are coming together. One here, another one here. And here's an example up here on the top. So this is where the earthquakes are, in this zone here. And this is where the trenches are and where the big volcanoes are, basically on the west side of Latin America. There are also divergent plate boundaries where plates spread apart. These are sometimes called spreading ridges or mid-ocean ridges. And there's one in the Atlantic and on the other side in the Pacific where two plates move apart. And then finally there's a transform plate boundary, which is where two plates move past each other. Strike, slip, fold. And we're gonna learn more about this as we go on. So mantle convection is this motion of Earth's interior, which is moving heat from the core, the hot core, to the solid surface. And there's a couple of ways this happens. One of them is hot material from deep in the mantle rises as what's called a mantle plume to make a hot spot. And that's, we'll talk about the Galapagos Islands in Latin America as a good example of that. And the other one is the cooling and sinking of dense lithosphere in what we call subduction zones. So there's one where the subducted lithosphere is sort of bottoming out at 670 kilometers. And here's another one that's going all the way to the core mantle boundary. These plates, as they sink, they do different things. But the geoscientists now understand that it's the sinking of dense lithosphere and subduction zones that drives plate tectonics, plate motions. All right, these are complicated topics. Let's watch a couple of videos. The first one that you'll see is about 4 minutes long.
Our home, the Earth, is unique. Look at photos of other rocky planets and larger moons in our solar system. They look very different than Earth in so many ways. Compared to Earth, they are more like big round rocks, without oceans and vegetation. They look so solid and uniform, you may think they're not as dynamic as Earth. But, in fact, they're dynamic as well. Their mantles are hot enough to allow the mantle to convect. We know that mantle convection exists in some other planets, like Venus and Mars, because we can see their surfaces are deformed and have volcanoes. Therefore, scientists say these are actively convecting bodies with tectonic activity, just like Earth. So why would these planets look so different from Earth? One big reason is that, unlike other planets with a one-piece rocky surface, Earth's outermost solid layer, what we call the lithosphere, is divided into many rigid plates that move independently on a hot, weak asthenosphere. These plates move and interact with each other to create various landscapes like folded mountain ranges and natural events like earthquakes. The theory that explains how these plates move is called plate tectonics, which is a special style of tectonics. To understand plate tectonics, we first need to understand what a plate is. If you've seen a map of all of Earth's plates, you would probably think this looks like pieces of a jigsaw puzzle. Well, they are, except these puzzle pieces don't sit still. They are slowly moving all the time. Although we are living on one of these plates, the North American plate, you'll never feel the movement. This is because the plates move very slowly. The fast plates move as fast as your hair grows, and the slow plates move as fast as your fingernails grow. Plates can move towards or away from each other, and they can also slide past each other. The different kinds of movement between the two plates creates different landscapes and forms different plate boundaries. There are 3 types of plate boundaries. Convergent plate boundaries occur where 2 plates move toward each other. These are where the highest and the lowest places on Earth can be found, such as Mount Everest and the Mariana Trench. Divergent plate boundaries occur where 2 plates move apart from each other, such as where ocean spreading ridges are. A good example is the Mid-Atlantic Ridge. Transform plate boundaries are where 2 plates slide sideways past each other. A good example is the San Andreas Fault of California. Plate tectonics is important for understanding the environments and natural events around us, and has played a critical role in nurturing life on Earth. Plate tectonics is a major reason why the Earth is so different from other worlds in our solar system.
Okay, I hope you learned a lot from that. This second video is about 5 minutes long.
To understand plate tectonics, we need to understand what a plate is. First, we should be clear that the term plate is short for tectonic plate, or lithospheric plate. In other words, plate, tectonic plate, and lithospheric plate indicate the same thing, the cracked pieces of Earth's outermost rigid layer, the lithosphere. you can imagine a cracked shell of a hard-boiled egg. Unlike an eggshell, however, what makes the plates is how the rocks behave rather than what they're made of. You may remember that the Earth has three major compositional layers: the core, the mantle, and the crust. One of the most confusing things about plate tectonics is the difference between Earth's crust and the tectonic plates. Many people confuse Earth's lithosphere with its crust. The crust is part of the lithosphere. But what you may not know is that most of the lithosphere is actually made of the uppermost part of the mantle that is cooler and more brittle than the hot, solid rock underneath. Crust and mantle are made of different kinds of rock, so have different chemical compositions, but together make the lithospheric plate. In short, a plate is a cracked piece of Earth's lithosphere and is composed of the crust and some of the upper mantle below it. In order to understand plate tectonics, it's also important to know that the Earth has two kinds of crust: continental and oceanic. Continental crust is thick and less dense, and so it rises higher and mostly is dry land above sea level. Oceanic crust is thinner and more dense, and so it is lower and usually hidden under the oceans. Because of these two very different kinds of crust, there are two different types of lithosphere: continental and oceanic. Oceanic lithosphere is more dense than continental lithosphere because its crust contains minerals with more heavy elements, like iron. A single plate can also be made of partly oceanic and partly continental lithosphere, such as the North American plates. A plate can also be entirely oceanic, such as the biggest one, the Pacific Plate. Oceanic lithosphere and oceanic crust are created by seafloor spreading at divergent plate boundaries. Divergent plate boundaries are where two plates move away from each other. Like the Mid-Atlantic Ridge or the East Pacific Rise. Typically, oceanic lithosphere is about 50 to 100 kilometers thick and can be even thinner at the ocean ridges where the temperatures are higher. Only the top 6 or 7 kilometers of the oceanic lithosphere is oceanic crust. The oldest oceanic lithosphere on Earth is about 180 million years old and was formed when dinosaurs roamed the continents. Oceanic lithosphere is dense enough to sink into the underlying mantle at convergent plate boundaries, where two plates move towards each other. Continental lithosphere is typically thicker and older than oceanic lithosphere. Some parts of the continental crust are billions of years old. So, now you know that a plate is just a piece of Earth's lithosphere. What the difference is between the crust and lithosphere, and what the difference is between oceanic and continental lithosphere. Now you may be wondering how they interact to make plate tectonics, or what evidence we look for on the surface to identify plate boundaries. Check out our next episode.
All right, so let's talk about the plates of plate tectonics. On Earth, there are 7 major and 6 minor plates. And so here you can see them all. The biggest plate is the Pacific Plate. And then the African Plate is the next biggest one. We're here in North America on the North American Plate. South America is on the South American Plate. You know, there's a lot of plates. Latin America is mostly on 3 plates. So there's the North American Plate, which includes Mexico and much of Central America. Then there's the Caribbean plate, which includes all the Caribbean and this part of Central America, and the South American plate that South America is on. All right, so here are the three main tectonic plates of Latin America. As we said, the North American plate, the Caribbean plate, the South American plate, and a little bit of Latin America is on a couple other plates. So Baja California is part of Latin America, and it's on the Pacific plate. And the Galapagos is on the Nazca plate. As we said, there are three types of plate boundaries. Where lithosphere is created, we call that a divergent or constructive plate boundary, like the mid-ocean ridges. Where lithosphere is destroyed, we call it a convergent plate boundary or a destructive plate boundary. And where lithosphere is neither created nor destroyed, we call a transform plate boundary. So here we see them again. Here we have a divergent plate boundary, and what you see is hot mantle generating magma that erupts along this mid-ocean ridge, and then that makes new oceanic crust, and then the lithosphere thickens to either side as these plates move away from the ridge. Here we have a convergent plate boundary that you can see the plate moving towards it, and then there's volcanoes above the subducted, we call this the subducted slab, the lithosphere that's being destroyed, and there's an oceanic trench, and not shown here, but there's lots of earthquakes in here. And also this is where a lot of ore deposits form, which, as you'll see later in this course, very important for the evolution of Latin America. And then a transform boundary is two things are moving past each other. So let's talk a little bit more about where lithosphere is created. And that would be, as we said, a divergent or a constructive plate boundary. Let's watch a 10-minute video.
Continents rupture and sometimes form new oceans. The elongated regions where continents break up are called rifts. Rifts affect the entire lithosphere, both the crust and the uppermost mantle. This video presents some basic information about how rifts form, how they sometimes evolve to become new oceans, and how passive continental margins form as a consequence. We briefly consider 4 examples of rifts around the globe. The East African Rift, both eastern and western branches. The Rhine-Graben of Europe, and 2 U.S. examples, the Basin and Range and the Rio Grande Rift. We then considered 2 examples of embryonic oceans, the Red Sea between Arabia and Africa, and the Gulf of California in northwest Mexico. We finish with 3 examples of passive continental margins, those around the Gulf of Mexico and those around the Central Atlantic Ocean, including offshore of the eastern United States and northwest Africa. Rifting is the focus thinning of the continental lithosphere. Lithosphere is the plate of plate tectonics and rides on hot, weak asthenosphere. Continental lithosphere consists of the continental crust, typically 40 kilometers thick, and the top 100 to 200 kilometers of the upper mantle. It is often mistakenly thought that only crust thins during rifting, but the mantle lithosphere must also thin. As rifting progresses, the lithosphere thins more and more, allowing the underlying asthenosphere to rise toward the surface and melt as a result of lowering pressure by a process known as decompression melting. These magmas rise toward the surface through and erupt as lava flows. Eventually, the lithosphere ruptures completely and seafloor spreading begins. Continents rift either because the lithosphere is pulled apart or because it is weakened from below by a mantle plume. These two end-member causes are called active rifts, those built over plumes, and passive rifts, those pulled apart by far-field stresses. Depending on the strength of the lithosphere, continental rifts may be narrow, less than 100 kilometers across, like the East African Rift, or wide, up to 1,000 kilometers across, like the basin and range of the western U.S. Narrow rifts form in cooler regions where the lithosphere is thick and strong, and wide rifts form in warmer regions where the lithosphere is thin and weak. As extension progresses, rifts evolve from subaerial to submarine. Through this evolution, rifts are defined by downfaulted regions, grabens, and uplifts, horsts, bounded by rift-length highs. Depending on climate, a through-going river may flow down the rift axis, as is seen for the Rheingraben, the Rio Grande Rift, and the western branch of the East African Rift. Or there may be terminal lakes with no outlet to the sea, as is seen for the eastern branch of the East African Rift and the Great Basin. Volcanic eruptions also occur during the early stages of rifting, so interbedded terrigenous sediments and lava flows are common in early rift deposits. Good examples of early rift and their deposits are found in the eastern U.S., including the asymmetric half-graben basins of the Newark series. These Triassic rift basins formed several tens of millions of years before seafloor spreading began to open the Atlantic Ocean and include some classic igneous rock localities, such as the Palisades Sill that overlooks the Hudson River in New York City, and the Watchung basalts of New York and New Jersey. They also contain coal deposits and lake sediments. Some rifts stop at this early stage, but others continue to widen. As extension progresses, the rifted region subsides and the sea invades, forming an embryonic ocean. At first, the seaway is narrow, and it is easy to block recharge from the larger ocean. A good example of this stage is the Red Sea, where extension has been going on for about 25 million years. The Gulf of California, where Baja California splintered away from Mexico, is another youthful example. In some cases, the embryonic ocean may repeatedly be flooded by seawater and then cut off from the sea, causing it to dry up repeatedly to form evaporite deposits such as halite and gypsum, as happened during the Jurassic opening of the Gulf of Mexico and the Miocene opening of the Red Sea. As the new ocean widens by seafloor spreading, free circulation of seawater with the larger ocean is established, ending evaporite deposition. Once an open seaway is established, normal marine sediments such as limestone and shale are deposited. The sequence of terrestrial sediment with lava, overlain by evaporites, overlain by marine sediments, is thus expected as a rift widens into an ocean. Changing sedimentation in an evolving rift is accompanied by a change in how subsidence happens. Early subsidence is controlled by faulting, and narrow grabens are filled with sediment and lava. Later subsidence is broader, caused by cooling and thickening of the lithosphere. This is the rift-to-drift transition, which is when continental rifting evolves into true seafloor spreading. Rifting may evolve rapidly to seafloor spreading, or it may evolve slowly to seafloor spreading, or it may stop suddenly and never become a new ocean. Every rift is different that way. The change in subsidence mechanism over the life of an evolving rift, from early faulting to late thermal subsidence is because, with time, the deformation and igneous activity migrates away from the original rift. In fact, this is not quite accurate. It is the two halves of the rift that migrate away from where seafloor spreading happens. These two complementary halves of the original rift subside to become passive continental margins, with an actively spreading mid-ocean ridge between them. Seafloor spreading turns the original one plate into two plates. Once seafloor spreading begins, the two halves of the original rift subside to become passive continental margins. The two complementary passive margins become part of the interiors of the two new plates and are increasingly separated with time. Two good examples can be seen in the passive margins of the eastern United States and Northwest Africa, which once were part of a single rift but which were separated beginning in Jurassic time. Today, the two sides of the Triassic-Jurassic rift are separated by the Atlantic Ocean. Each half has part of the buried rift overlain by the rift sequence: terrestrial sediments and lava, evaporites, and marine sediments. Passive continental margins contrast with active margins like transform faults, where two plates slide past each other, or convergent plate boundaries, where one plate subducts beneath another. Instead, passive continental margins lie in the interior of plates but are nevertheless important because they are boundaries between continental and oceanic crust. Because great rivers flow from continental interiors to the sea, passive continental margins are where most sediment is deposited. Important cities have grown up where great rivers flow into the sea. For example, New York City, Houston, London, Mumbai, Hong Kong, Shanghai, and Amsterdam. And much of the world's population lives on passive continental margins. These huge piles of sediment also host important deposits of oil and natural gas. We hope this brief overview of continental rifts, young oceans, and passive continental margins, and how these are related has been informative. Keep some of these concepts in mind the next time you enjoy a day at the beach. The wide beaches, like those of Texas and Florida, are most people's favorite experiences with passive margins.
I hope you enjoyed that. Okay, here is a good map of the mid-ocean ridge system. And you can see that Latin America has got a number of divergent plate boundaries. On the east side, we have the Mid-Atlantic Ridge. On the west side, we have the East Pacific Rise, which actually goes up the Gulf of California and splits Baja California off from Mexico. Then we have the Galapagos spreading ridge in here, and the Chile Rise in here. So Latin America has got plenty of divergent plate boundaries surrounding it. So these mid-ocean ridges, these divergent plate boundaries, are mostly submarine. We need to study them with research submarines like the Alvin. And if we go down there, we can see some really interesting things in places. These hydrothermal vents with it's not really smoke, but it looks like smoke coming out of these vents. And this is called a black smoker. You've probably seen stuff on Discovery Channel about it. So because of the Mid-Atlantic Ridge divergent plate boundaries, South America is moving away from Africa at about 17 millimeters a year, about 3/4 of an inch. Now, it may not have escaped your notice that if you put, it looks like South America and Africa could sort of fit into each other, and that is true. They were originally joined, and we'll talk more about this later in the course. So here we can see the age of seafloor as a function. So this red is very, very young. And that's the divergent plate boundary. It goes all the way up here, up to Iceland. And so that's where the plates are, a new plate material is forming and the plates are spreading apart. And then over here on the side is much older seafloor. And so you basically, the age of the seafloor increases either direction from the divergent plate margin. Very simple. So let's go back to the spreading ridges, the divergent plate boundaries around Latin America. There are 6 of them. We've talked about the Mid-Atlantic Ridge. We haven't really mentioned the South Sandwich Ridge, but it's in here. There's the East Pacific Rise, which is like the Mid-Atlantic Ridge, but it's on the east side of the Pacific. Doesn't go down the middle of the ocean like it does in the Atlantic. There's the Chile Ridge, comes in here like this. There's the Cocos Ridge, comes in here like this. And then there's a little ridge in here, you can't hardly see it. It's called the Cayman Trough. It's the shortest spreading ridge on the planet. All right, now, one of the things that plate tectonics does is it gives us 2 kinds of crust. One of them is oceanic crust, and the other is continental crust. So oceanic crust is thin, only 6 kilometers, 4 miles thick, whereas continental crust is much thicker, 40 kilometers or so. And the other difference is that oceanic crust is denser at 3 grams per cubic centimeter than continental crust, which is 2.7 grams per cubic centimeter. Just for reference, water is 1 gram per cubic centimeter. So this is thinner and denser. This is thicker and lighter. They both lie on mantle that's very similar. But as a result, this kind of crust stands high, and this kind of crust stays low, and it gets flooded by water. Oceanic crust, unsurprisingly, is all mostly in the oceans. Continental crust is on the continents. That's where people live. The geology of Latin America is focused on what's on top of this, but some of the geology and the ore deposits and the earthquakes and the volcanoes have to do with what this is doing, interacting with this. All right, now another concept that comes out of plate tectonics is the idea of a passive margin. So we talked about 3 types of plate margins: convergent, divergent, and transform. A passive margin is not a plate boundary, it is a crustal boundary. A little bit complicated, but basically as you go from on land to the oceans, you have a change in crustal type. And that change in crustal type results in a place where a lot of interesting things happen. So here we see a passive margin, a passive continental margin. And this is what a mature one looks like. And this is how it evolves. It starts off as a rift in the middle of a continent, and then slowly, as this spreading ridge develops, the 2 sides are taken away from each other, like we see with the east coast of South America and the west coast of Africa. And both sides develop something like this, and the older they get, the more this region subsides and the more sediments dump on it, and you get very thick sediments. Okay? So we see a lot of those around especially the Atlantic. So here, all of the passive continental margins, there's one on West Africa, there's the one on eastern South America. We've got some on the Gulf of Mexico and on the east coast of the United States. And in contrast, the margins of the Americas with the Pacific Ocean are not passive continental margins. They're a very different kind of margin. Next slide. All right, so let's talk about that margin on the west side of Latin America. These are convergent plate boundaries, destructive plate boundaries, and let's watch a short video about that.
In past episodes, we learned that plates are fragments of Earth's lithosphere. And there are 2 different kinds of plates: oceanic and continental. Plates move independently and interact to shape landscapes and cause earthquakes, than volcanic eruptions. Can you guess how many different types of movement there can be? The answer is 3. Plates can move towards each other at convergent plate boundaries, away from each other at divergent plate boundaries, and slide past each other at transform boundaries. Plate boundaries have the most earthquakes and volcanoes. In this episode, we're going to focus on convergent plate boundaries. A convergent plate boundary is the meeting place of two plates converging, which just means moving towards each other. Where they meet, one of the plates will sink or subduct beneath the other. There are 2 different types of convergent margins, depending on whether the subducting plate is continental or oceanic. If a continental plate subducts beneath another continental plate, we have a collision zone, where continental crust is folded, faulted, and pushed under the other plate, creating mountain ranges like the Himalayas. These mountain ranges are the highest places on planet Earth. In contrast, where an oceanic plate subducts beneath another continental or oceanic plate, an oceanic trench forms. Trenches are the deepest places on Earth's surface. Let's talk about the subduction of oceanic crust first, and then we'll talk about continental collision zones. There are 3 important features of convergent margins that subduct oceanic plates: trenches, earthquakes, and volcanoes. Trenches are where the oceanic plate begins to subduct. The deepest earthquakes in the Earth happen beneath convergent margins. These earthquakes define an inclined seismic zone that tells us where the subducted oceanic plate is. A chain of volcanoes is also found above the subduction zone. These volcanoes are called an island arc if they are found in the ocean, like the islands of Japan, the Philippines, or Indonesia. Continental margin volcanoes also make high mountains on land, like the Andes of South America or the Cascade volcanoes of Oregon and Washington. Convergent margins subducting oceanic crust are especially important around the Pacific Ocean, and the many volcanoes associated with these are part of what is called the Ring of Fire. Regions around convergent plate margins can be dangerous because of the strong earthquakes and violent volcanic eruptions. Very powerful earthquakes can happen in the subduction zone, including the 2011 earthquake that struck Japan. Sometimes these strong earthquakes happen under the ocean, and this can cause a devastating tsunami. The second type of convergent boundary is when 2 continental plates meet, causing a continental collision. Remember, the continental plates are lighter and thicker, so it is really hard for continental plates to sink into the mantle. Have you ever tried to push a ball underwater? The ball will rise to the surface and float because it's filled with air, which is less dense than water. Just like the ball in the swimming pool, the lower density continental plates are not easy to subduct into the mantle. Instead of going down, the continental crust literally bunches up, thickening and folding to create spectacular mountain ranges. Like the Himalayas or the Alps. Mount Everest is the highest mountain in the world and formed as a result of the collision between the Indian and Asian continental plates. These mountain ranges are not only high, but are some of the most beautiful places on Earth. In the next episode, we visit spreading centers and see how plates are born. See you next time when we will talk about divergent plate boundaries.
I hope you enjoyed that video. Now, so we're talking about convergent plate margins or destructive plate boundaries, and these are where plates go to die. Rest in peace, plate. And these are associated with four main geological features: subduction zones, deep earthquakes, oceanic trenches, and volcanic arcs. So these are all related with convergent plate boundaries. And they're some of the most exciting things that happen in the Earth. So here's a very simplified diagram of a convergent plate boundary. So this is the one plate is being destroyed, subducting in this region. And this is the overriding plate. This would be South America. This would be the Pacific or the Nazca plate subducting underneath western South America. There's a trench. There's a volcano, and there's a zone of melting above the downgoing lithospheric slab that causes melting. And there's a lot of earthquakes as a result of this sinking in the mantle. So there's about 55,000 kilometers of convergent plate margins. It looks like the seam of a baseball. That basically, wherever there's a spreading ridge, there has to be at least one convergent plate margin for that oceanic lithosphere to be consumed. Next slide. Let's talk about the earthquakes. So earthquakes are one of the important things that convergent plate margins give you. Next slide. Here we're looking at a cross-section of the Earth down to about 250 kilometers deep in the Earth. Not very deep. And we're looking at a region across the north, the island of Honshu in the Western Pacific. And the Japanese are obviously very interested in earthquakes because they have so many, and they have mapped them out in great detail. All of these little dots are hypocenters, basically earthquakes that happened over different times. And you can see there's a region up here with shallow earthquakes, less than about 30 kilometers deep. And here we've got what's called the volcanic front. That's basically where the volcanoes of Japan are. And you can see this is defining as dipping zone of earthquakes. And that's how we know what the subducted slab is doing. These earthquakes are basically telling us of its motions going down into the Earth, back into the Earth. Now, if we look at the earthquakes of Latin America, they are not scattered over the region. They are concentrated on the western side, very few on the eastern side, and that's because of plate tectonics. The Nazca plate, which is here, and the Pacific plate, which is here, is subducting eastward underneath western South America. And you see here all of these different colors. Those are telling you about the depth of the earthquake. So 0 to 33 kilometers is red, yellow is 33 to 71, green is 71 to 151, blue is down to 300, purple down to 500, and red ones are ultra deep, down to 800. And so there's actually two kinds of reds. These are shallow ones here. These are deep ones over here. And so you get a sense of this dipping seismic zone beneath western South America. So you can see that the people of Colombia, and Ecuador, and Peru, and Chile, and western Argentina are very concerned about earthquakes. The people of Brazil, much less so. Next slide. All right, so there's lots of earthquakes in western Latin America, and some of the biggest ones that have ever happened there. So these are the largest earthquakes in the Earth that has happened since 1900, about when we started being able to measure earthquake locations and magnitude. And you can see a lot of the big ones are along the western margin of Latin America. So these things around the Pacific, you know, Latin America, the Aleutians in Alaska, Japan, you know, those regions are all very sensitive to earthquakes because they're all on convergent plate boundaries. Next slide. All right, the next thing we have is trenches. Remember, on the eastern side of Latin America, we have this passive continental margin over here with thick sediments. On the western side, we have a deep region called an oceanic trench. And so these regions get much deeper than the rest of the ocean. So for, you know, just for comparison, the Challenger Deep in the Western Pacific is almost 11 kilometers deep. It's the deepest trench in the world. But the ones around Latin America are pretty good too. The Puerto Rico Trench up here in the northern part of the Caribbean is the deepest one around Latin America at 8,600 meters. The Middle America Trench gets down to 6,600 kilometers. The Peru-Chile Trench gets down to almost 8,200 meters. And the South Sandwich Trench down here is over 8,300 meters, which is, you know, twice as deep or more than the average seafloor depth of 3,700 meters. Okay? And the last thing that's associated with convergent plate margins are volcanoes. So volcanoes are associated with the subducting slab, but Latin America has a very interesting distribution of volcanoes that we'll talk about more in this class. So basically, Latin America, the western side, is part of what they call the Circum-Pacific Ring of Fire, which goes all the way around the Pacific, ends up down here in New Zealand. And these volcanoes are on the west side of South America, all through Central America and Mexico, and they're also over here, but they're sort of out in the Atlantic in a funny way, and down here in the South Sandwiches. Next slide. So here are the main arc volcanoes of Latin America. And we say arc, you might be going, what do you mean arc? It sounds like a geometric term. And we call them arc volcanoes because very often convergent plate margins are curved like an arc of a circle. But now we associate them with just any kind of convergent plate boundary. So there are volcanoes up here through Mexico and Central America. There's ones over here in the Lesser Antilles. And then there's three big belts in South America. There's one up here in Ecuador and Colombia, and there's a big gap where there's no volcanoes, and then they're down here in southern Peru and northern Chile, and then down here in southern Chile, and then over here in the South Scotia Arc. So we talk about these kinds of volcanoes, these kinds of arc volcanoes, as Andean type arcs. So not to get too much into the weeds, but there are volcanoes that are not very tall that are built on oceanic lithosphere out in the western Pacific. But these volcanoes in the west side of South America are extremely tall because they're built on continental crust. So the volcanoes are tall and they're built on thick, high-standing crust. And so some of these arc volcanoes built on continental crust represent some of the most spectacular volcanoes that you can study. And they're associated with ore deposits that we'll be talking about too later in the class. So one of the most spectacular eruptions happened in the Lesser Antilles. So this is the Lesser Antilles on the eastern side of the Caribbean plate. There's Cuba, there's South America. And there's a whole bunch of volcanoes in here. And one of them erupted in 1902, and Mount Pelée, and killed 29,000 people in a single eruption, almost before they knew what happened to them. By the biggest volcanic disaster, I believe, in the history of the world. We'll see if that's true or not later. Now, another thing that happens is because subduction zones and convergent plate boundaries tend to exist for long periods of time, these magmatic systems that come from deep in the mantle above the subducted plate set up magmatic plumbing systems that can get quite complicated. So here we've got a volcano like we talked about, and it's erupting ash and stuff. And underneath it is an entire subterranean world of igneous intrusions. As magma comes in, some of it eventually erupts, but some of it doesn't and stays down here. You get all sorts of things like gases coming off that can carry economic deposit, minerals, elements with them that can make ore deposits that we'll talk about. But you get things that at great depth that we can't see while the volcano is erupting because we're covered by this thing. But if we're patient and wait a few 100 million years, erosion will remove all of this junk and we'll get to see them directly. So here we've got one of the most famous examples of the eroded roots of an ancient volcanic arc, which is Half Dome in the Yosemite Valley of California. And you have to imagine, several kilometers of volcanic material has been stripped off, and now we're looking down at what used to be the super hot magmatic regions underneath this big volcanic arc. That volcanic arc was active 100 million years ago, and it's taken that long for all of this overlying volcanic material to be removed. So we've seen this before. Oceanic crust is thin and dense. Continental crust is thick and buoyant. And we see this in the geology of Latin America. So here we are in Dallas giving this course, and just to give you an idea of the geology of Dallas, if we went down through the crust, about 45 kilometers or so, down into the mantle, this is what we go through. So we're up here on top of Cretaceous sediments. They're about 100 million years old. And then underneath them are Paleozoic sediments, more like 300 million years old. And then underneath them would be some older volcanics, about 1.4 billion years old. And then some granitic material of the upper crust, and then some other material of the lower crust. Basically, that's the geology. So sometimes you have these igneous rocks right at the surface, and sometimes they're covered by a little bit of sediments, like we have in Dallas. So here we see the crust of the world. So what you'll see is, first of all, we talked about oceanic crust being about 6 kilometers thick. So in the oceans, it's everywhere thinner than 10 kilometers, right? All of this in here is less than 10 kilometers, except up here in Iceland where it gets to be thicker. But generally speaking, the oceans are all, as we said, 6 kilometers or so. But the continents, that crust is typically 40 kilometers thick. Sometimes it gets a little thicker, sometimes a little thinner. But I want to draw your attention to two places where the crust gets super thick. And the thickest region of continental crust in the world is the Tibetan Plateau, where that crust gets 70 kilometers thick. And the second thickest crust in the world is here beneath western South America, in what's called the Altiplano region. So thick crust usually stands high. The Tibetan Plateau is the highest plateau in the world. The Altiplano is the second highest. So here is the Altiplano. This is in the Andes. This orange region is all the mountainous region of the Andes. And here in the Altiplano, it's actually a closed basin. And there's a lot of interesting things that go on here geologically. There's these big lakes that here, Lake Titicaca, and then there are some dry regions called salars, which we'll talk about more. So the Altiplano is a high plateau, inland drainage in the central Andes. It occupies parts of northern Chile and Argentina, western Bolivia, southern Peru, and it's up to typically around 3,700 meters tall, slightly less than the Tibetan Plateau. So, why are the Andes so high? The mountains of the central Andes are the second highest range in the world. The Himalayas, of course, are the highest, with 100 peaks taller than 8,300 meters. The Andes have 84 peaks taller than 6,000 meters, which is, generally much taller than anything we have in North America. And the reason is because the crust of the Central Andes is the second thickest in the world. Thick crust means high mountains. And this brings us to a concept called isostasy, which tries to explain why thicker crust stands higher. So what is isostasy? So it's a Greek word for equal standing, and that it indicates that masses will be equivalent above some compensation depth, which could be the asthenosphere. And so the question is, how can there be different elevations of Earth's solid surface? So here we have two models. These are 19th century models by two geophysicists. One was called Pratt and the other was called Airy. And Pratt argued that what you've got are different densities of crust, and so that, here we see the densities. The least dense is this thing. It's only 5,000 density units, whereas this lead is 11,000. So this mass in here is equivalent to this mass in weight. And so that is what's determining which one stands taller. The lighter it is, the higher it'll stand. Now, Airy said, no, that's completely nonsense. What it is the continental crust is all the same density and there's different thicknesses. So that where you have the highest standing region, you must have the thickest crust. And where you have the lowest standing region, you must have the thinnest crust. To a first order, this is what we see in Latin America, in South America. The Andes are the region of the thickest crust, and they are the highest standing region. Next slide. All right, so let's talk about the third type of plate boundary, which is the transform plate boundary. Let's watch a 6-minute video.
In past episodes, we've talked about convergent and divergent plate boundaries. Seafloor spreading creates new oceanic lithosphere at mid-ocean ridges that occur at true divergent plate boundaries. And this creation is balanced by destruction of old oceanic lithosphere at convergent plate boundaries. These two types of plate boundaries are marked with ridges and trenches and explain the birth and death of the plates. However, if we project these plate boundaries on the map, we can see there are gaps in the outline of the plates. There must be another kind of plate boundary. The third type of plate boundary is called a transform plate boundary and is marked by transform faults. Transform plate boundaries don't create or destroy lithosphere. Instead, transform faults allow oceanic plates to slide past each other. Transform faults can connect with either divergent or convergent plate boundaries. There are many transform plate boundaries all around the world, both on land and in the oceans, just as there are for other types of plate boundaries. Transform plate boundaries can therefore be subdivided into two groups, oceanic and continental transform plate boundaries. Let's talk about continental transform boundaries first. The San Andreas Fault in California is the only transform plate boundary in the United States and is one of the most famous in the world. This transform fault can be traced for 750 miles or 1,200 kilometers from near the border with Mexico to north of San Francisco, where it continues on the sea floor. The San Andreas Fault connects two divergent plate boundaries, the East Pacific Rise in the south with the Juan de Fuca Ridge in the north. The San Andreas Fault separates two of the Earth's biggest plates, the Pacific Plate in the west and the North American Plate in the east. The fault is often easy to see because it makes long, straight depressions and uplifts. Depressions along the fault are often filled with water to form long, narrow lakes or bays. You might have heard an idea that California west of the fault might fall off into the ocean. Because of how transform faults work, this would never happen. However, at the slow rate of about 5 centimeters each year, the western side is moving north as the two plates slide past each other. Over millions of years, rocks that formed in Southern California have moved to Northern California. Because of their side-by-side style of motion, transform plate boundaries are different than the other plate boundaries in that they don't produce volcanoes. However, like the other types of plate boundaries, they do produce earthquakes. Earthquakes happen when there is motion along a fault. Small amounts of motion cause small earthquakes, and large amounts of motion cause big earthquakes. About 10,000 earthquakes happen along the San Andreas Fault every year, but most are so small they're not even felt by people nearby. Large earthquakes happen less often, but when they do, they can cause a lot of problems. Because cities like San Francisco and Los Angeles lie near the San Andreas Fault, big earthquakes along it can cause a lot of damage. Such a big earthquake happened in 1906 near San Francisco, killing 3,000 people and leaving half of the city's 400,000 people homeless. A much more deadly earthquake struck the Caribbean island of Haiti in 2010. Haiti lies near a transform fault boundary between the North American plate to the north and the Caribbean plate to the south. Buildings were not designed to survive such an earthquake, and many collapsed. Over 100,000 people died as a result of this terrible earthquake. People that live near transform faults need to be prepared for big earthquakes. Oceanic transform faults are also important. The most spectacular examples of oceanic transform faults are found in the Mid-Atlantic Ridge between Africa and South America. These connect the spreading ridge and divergent plate boundary in the northern Atlantic Ocean with the spreading ridge and divergent plate boundary in the South Atlantic. The northern and southern parts of the Atlantic Ocean open separately, and these oceanic transform faults connect them. The offset of the divergent plate boundaries, farther west in the north, farther east in the south, was accompanied by these oceanic transform faults. The difference in the position of the spreading ridges in the Atlantic Ocean is also what causes the shoreline in the southern part of West Africa to trend east-west, parallel to the oceanic transform faults of the region. There are many other examples of transform plate boundaries around the world. Take a look at a map and see if you can find the one in New Zealand and between Israel and Jordan. They're not hard to find, just follow the plate boundaries. Now we have covered 3 types of plate boundaries: convergent, divergent, and transform. In the next episode, we will talk about how scientists came up with the theory of plate tectonics. See you next time.
Okay, I hope you enjoyed that. So here's an example of a transform plate margin. Here there's the San Andreas Fault, which goes right through San Francisco and then comes into Latin America, and then it joins up with the spreading centers here in Baja, in what's called the Gulf of California, and that's Baja, California. Next slide. So Latin America has some very interesting transform plate boundaries. So especially on the north and south sides of the Caribbean. Now this is a confusing diagram, but what we've got here is a transform margin that has some interesting things and comes along the south side of Cuba. Cuba is part of Latin America, but it's also part of the North American plate because this is the plate boundary for the Caribbean. And then it comes through Haiti. Haiti had a very deadly earthquake that we'll talk a little bit about. Dominican Republic on the north side of Puerto Rico, and then it joins up with this convergent plate margin here, where the Atlantic is being subducted underneath the Lesser Antilles. And then on the south side of the Caribbean, we have a very interesting complex set of structures related to this transform boundary in here as well. So the final thing we want to talk about is mantle plumes and hotspot volcanoes. So these are basically regions that are not necessarily on a plate boundary. They can be, like Iceland, or they can be out in the middle of the plate. And so they can occur anywhere within a plate or along a divergent plate boundary. They're caused by upwelling mantle material from deep in the mantle. This melts and generates a lot of basalt, and it sometimes produces chains of volcanoes, volcanic islands, or seamounts. So here we've got an example of a mantle plume. You can see it coming here from near the core, rising up to the lithosphere where it erupts, and here we zoom in. There's the plume, that's the magma. Now this plate is moving so that the region of melt periodically is going to have to go too far, bend over to get to the volcano. So a new volcano will form here instead, downstream of the main one. So sometimes you'll see trails of volcanoes that will record the motion of the plate over this fixed hotspot. So here we got the most spectacular one. Hawaii is where the volcano is, and this chain, which goes through the Hawaiian Islands and then into a long chain of seamounts, is basically the scar of this hotspot. And as you go in this direction, every volcano gets older and older till this one up here is about 100 million years old. And this shows you over here how it happens. So here's the first volcano sitting on this plate that's moving that direction. It moves too far, so a new volcano has to form, and then the plate keeps moving, and a new one, plate keeps moving, and a new one. All right, the most famous, well-known hotspot is the Galapagos. So the Galapagos are offshore Ecuador, just south of a spreading ridge between the Nazca and the Cocos plates. And it's a group of islands, all with a very interesting set of names. Here you can see it from space. And this is the region where you've got some very interesting creatures. And it belongs to Ecuador, by the way. So this is a very interesting place, important place in science, because this is where Charles Darwin noticed the remarkable adaptations that the animals of the Galapagos were doing. The Galapagos are something that formed very recently. It was not easy for animals to get there, land animals in particular, but as soon as they did, they occupied the available niches and evolved in very, very interesting ways. So this brings us to the Galapagos tourism. Most people would like to take a vacation and see some of the remarkable things that Charles Darwin saw. For example, these incredible tortoises. And it brings up an interesting point in talking about Latin America, is the importance of tourism. Tourism is very important for especially developing countries because it is so important for reducing domestic poverty. And tourism today is responsible for about 5% of the world's GDP, and it helps provide foreign exchange earnings and 235 million jobs. And many of these jobs belong to poor people in developing countries because of the labor-intensive and low-skill nature of work in the tourism sector. So, you know, we're not going to talk a lot about tourism in Latin America, but I think all of you may develop an interest to visit there sometime. And if you do, you'll not only be enriching yourself through your experiences, but you'll also be helping the economies of these countries, many of which are still developing. Okay, so here is the Galapagos Hotspot Trail. Galapagos Islands are over here, and the Nazca Plate has been moving eastward to subduct underneath South America, and here is its hotspot trail, you know, and this region gets older to the east. There's another trail that goes off to the northeast called the Cocos Ridge. Anyway, thank you. And next lecture, we're going to talk about more details about the geologic evolution of Latin America, building on what we learned today. So, have a good one.